morning everyone. Today we will be discussing about the magnetism, superconductivity and the Bose-Einstein statistics, and this is about the last week lectures. And so let us start with magnetism. So magnetism is an experimentally observed phenomena in which materials exert certain kind of attractive or repulsive force. Certain kind of attractive or repulsive force based on their polarization and based on certain properties. So these are the materials are usually electrically neutral samples, and they have quite a number of use in audio speakers, motors, and they are very commonly found and have lot of technological applications. And there are certain big equipments like sophisticated equipments, for example NMR, which is used quite NMR which use magnetism. And there are other fields in medical sciences and even in fundamental physics and all, where magnetism is quite used a lot. So we define something called magnetic field strength to quantify the magnetism. So what this magnetic field strength is? So it is an experimental handle that an experimentalist has to force a certain material into to probe the magnetic property of certain kind of material. So it is an externally generated magnetic field, and this is what the experimentally has on his hands. Like he has the control over this magnetic field strength. And how this is controlled? Like suppose if you have and this is controlled with the magnet movement of charges. So if you have a coil, and let's say that coil has n turns, and the length of the coil is L, so that means n turns in length L, then and you are passing current I through this coil. So the magnetic field strength, which is denoted by H, is given as N times I. So N is the number of turns, I is the current, and L is the length. So N I over L. This is your magnetic field strength, and this is a unit of amperes turns per meter. Or turns is unitless, number of turns is unitless. So you can just the unit will be just ampere per meter. So now what will happen to a material if it is exposed to that H field? So the material will acquire a magnetic induction or a magnetic flux density B, which has a unit of Weber per meter square, and it is related with H through a quantity which is dependent on the material. So so actually this H field, it is a directional field, and the direction of it is given as so you take a cross product of, you take the curl of the current, and if you rotate the current with your right hand fingers, then the direction of your thumb, so if the current is passing like this, you rotate your fingers in the direction of your four fingers in the direction of your current, then the direction of the thumb will tell you what is the magnetic field. So H is a vector quantity, and when you multiply it with permeability of the material, permeability is the quantity, material quantity, which will tell you about the magnetic response of the material. So what you get is the magnetic field induction or the magnetic flux density, and it has a unit of Weber per ampere per meter. So and Weber per ampere is also called Henry. So the unit of mu is Henry per meter. In vacuum, we have this quantity called permeability of vacuum. The magnetic field induction in vacuum, when there is no material present, it is called magnetic. The magnetic field, mu at that particular point of time is called the permeability of vacuum. In the case where you don't have a material in that coil, and mu naught has a value of 4 pi into 10 to the power minus 7 Henry per meter. So we define something called relative permeability. So in the case where we have vacuum, we have this quantity mu naught. But when we have certain material, then the response is different from the vacuum. The magnetic response is different from the vacuum. And how different it is, that is taken by that is given by the ratio mu over mu naught. That is mu r, and it is, since it has this mu has a unit of Henry per meter, they will cancel in numerator and denominator, and mu r, which is the relative permeability, it is unitless. So the this mu r is something that will tell you about the material with respect to the vacuum. Now, so we discussed that mu r is something which tells you about the material with respect to the vacuum. Now we define something called magnetization, which is actually the response of the material, and it is denoted by this m vector here, m vector, and b, which is equal to mu times h. This can be written as the sum of two components. One is mu naught h plus mu naught m vector, and this comes from the material, and mu naught h, as we discussed, this comes from the vacuum. So in a material, the contribution can be decomposed into a vacuum contribution and the material contribution. The material contribution, which comes from this m vector, that can be written as, it is related to h by something called a susceptibility, a magnetic susceptibility, which is chi times h. In most cases, when the material is linear, what we have is this m is directly proportional to h and chi is a constant. This is called this chi is called the magnetic susceptibility. And if you take the h common, so it will be mu naught 1 plus chi times h. So what we have is b is equal to mu h is equal to, and this we decomposed into mu naught h plus mu naught m, and mu naught m we are writing it as mu naught chi times h. Then mu naught we are taking common, and 1 plus chi as so 1 plus chi we are taking a common, and what we have is h. So from here what we can see is that the relative so mu is equal to mu naught 1 plus chi. So mu r, which is nothing but the ratio of mu over mu naught, is 1 plus chi, or chi, which is the magnetic susceptibility, is given by 1 minus mu r. So in case of vacuum, we saw that h equal to ni over l, and b equal to mu naught h, and mu r is mu over mu naught. So these are the so when we know these quantities, either h is the what we probe experimentally, we can give subject a material to this h field. B is what we develop by virtue of this mu r. So let us now go into some of the reason of magnetism. So most of the magnetic contribution, it comes from that of electron. The electron can be in certain orbital moment. From there we can get something called the orbital angular momentum, and so from there we can get some magnetic moment. So it is just nothing but, so in the case of coil, we saw we are deliberately moving, we are deliberately injecting some charge into the coil, and it is because of that motion of the charges, it caused the magnetic field to be produced. So in atoms and atomic systems, what will happen is this electron can be in certain type of orbital motion, and thereby creating very small like currents in that small regions, and that will create a magnetic moment. Another fundamental reason why a magnetic moment is there is the electron spin. And uh, the fundamental unit of magnetic moment is called Bohr magneton for 1 unit of magnetic spin. So it is that mu b is 9.27 into 10 to the power minus 24 Weber per meter square. So orbital magnetic moment is mi times mu b, and this is a vector quantity. Mu b is again it is the Bohr magneton, and it is the magnetic quantum number. Mi is the magnetic quantum number of the electron. So what happens in a particular material is that we identify all the sources of magnetism from a material and then add them vectorially to see if we have certain magnetism or not. So the spin can contribute, like let's say if it is a plus half spin, it can give plus mu b, and minus half spin means minus mu b. The net magnetic moment for atoms is fully filled with fully filled cells will be 0, because the spin up particles and the spin down particles, they will have opposite magnetic moment, and therefore uh, they will cancel each other because it is a vector sum of this magnetic field, and they will give 0. And all the contributions of orbital magnetic moment will also cancel each other, and all the contribution of spin magnetic moment will also cancel each other when the atoms are fully filled cells. Now there are different types of magnetism. So one of the type is diamagnetism. It is a very extremely weak phenomena, and this occurs only when there is an external field. If you remove the external field, this phenomena will not be there. So what is this phenomena? So if you give a magnetic field like that of if you give a magnetic field, then the material will try to oppose that magnetic field, and the resultant magnetic field will be less than that of the vacuum. So it will weakly, but that opposition is very very weak. So the contribution, so it will weakly oppose to the applied magnetic field, and the contribution for orbital angular moment, and and it has a contribution from the orbital angular momentum of the atoms. And because the magnetic field is less than that of vacuum, you have mu r is less than 1, and mu r is what? It is 1 plus chi. 1 plus chi is less than 1. The only way this can happen is chi is equal to mu r minus 1, and mu r is less than 1, so it is a negative quantity. But the value of chi, it is of the order of, and you remember that chi has to be unitless because mu r is unitless. So chi, or the magnetic susceptibility, is of the order of minus 10 to the power minus 7. It is a very weak phenomena, and it is present in all the material. So this phenomena is present in all the material. Next is something called paramagnetism. So the net cancelled magnetic moment of the net. So here you have, if you have some unfilled cells, then the net magnetic moment will not be totally cancelled. So the net uncancelled magnetic moment either of spin or orbital angular momentum per atom on a per atom basis is non-zero. Yeah, so the sample will have magnetic moment in absence of so when you have the field, you will have the paramagnetism, but when you have no field, you will not have the paramagnetism. And in this phenomena, if you have certain magnetic field, the external field, then the uncancelled magnetic moment will try to align itself in the direction of magnetic field, and because of this alignment, you will have the net magnetic field in the material to be greater than the vacuum. So mu is greater than mu naught. So mu r, which is the ratio of mu by mu naught, is greater than 1. So chi is mu r minus 1, and mu r is greater than 1. That is why chi is positive. And this is also a very weak phenomena, and it is present only in the presence of an external magnetic field, and it has the order of 10 to the power minus 7, but it is a positive quantity. And this happens because of alignment of the uncancelled magnetic moments. So this diamagnetism and paramagnetism, this exists in the presence of an externally applied field. Thus, paramagnetic and diamagnetic materials are also called non-magnetic materials. And since they are very weak phenomena, they are not of very great significance in terms of technology. Then there is something called ferromagnetic materials. Here, the uncancelled spin magnetic moment can cooperatively arrange themselves so that there is a net magnetic moment even in the absence of a magnetic field. So there is a kind of self-assembly happening, or self-organization, or self-ordering is happening, which is causing a net magnetic moment even in the presence of a vacuum contribution. Even in yeah, so B, which is equal to mu naught H plus mu naught M. This mu naught H, it is very weak phenomena, as we have seen earlier, and this quantity, because of that self ordering of the uncancelled magnetic moments, this quantity becomes so large that you can virtually neglect this term. This is very large term. So B is approximately equal to mu naught times M, and chi, it is 1 plus mu r, and mu r is of the order, it is so large that mu r is 10 to the power 6. So remember that earlier mu r was of the mu, it was of the value of 10 to the power minus 6, but 10 to the power minus 7. But now we have this value of the order of 10 to the power 6, which is really very dominating term, making it a very dominating term. And this ferromagnetic material results in something called the permanent magnets that we see in everyday life. So if you have, if you want to plot B versus H for different materials, so in the vacuum the black line shows B equal to mu naught H. The slope of B and H will give your permeability. For diamagnetic materials, the slope will be little less than vacuum, and for the paramagnetic materials the slope will be little more than the vacuum. Okay, but for the ferromagnetic material, the slope is very large than that of the, it is very large than that of the vacuum. So now, so what is this ferromagnetic material? It is resulted from the self organization of individual magnetic moment. But if they align in such a way that there is a complete cancellation of the magnetic moment, for example here you see there is a complete ordering, as well as what is happening is there is the magnitude of the upward magnetic moment is same as the magnitude of downward magnetic moment, which results in cancellation of this magnetic field entirely. And this type of material, which is ferromagnetic, but since there is no magnetization as such, we call it anti-ferromagnetic material. Okay, now other thing that can happen is there can be ordering, but the opposite magnetic moments do not cancel each other perfectly. Those kind of material are called ferrimagnetic material. Now if you do an experiment, you apply H and you measure what is the value of B. So when we do that experiment, first when we increase the value of H, then B will also increase based on what is the material, and it will reach a uh, certain value of uh, magnetic field induction for a given magnetic field strength. Then when you you start reducing the magnetic field strength. So when you start reducing, it will not follow the same path as the magnetic field induction in that material will not follow the same path as it as it reached this particular B. It will reduce in a slower rate. But when your H is 0, Yeah, but when your H is 0, so what we're doing is, so in this experiment what we are doing, we are increasing H, and yeah, so in this experiment what we are doing, we we are increasing H and then decreasing H and then again coming back to the zero magnetic field strength. And in this cycle of changing the magnetic field strength, we are trying to measure what is the magnetic field induction. So when we start increasing the magnetic field strength, then we will reach a certain value of magnetic field induction. But when we start reducing the H again and come back to 0, it will not, the first point is that it will not take the same path, and there will be certain amount of magnetic field induction which will be remaining even if the um, magnetic field strength is 0. So that magnetic field induction is called the reminiscence of that material. Now when we start opposing the magnetic, so now we apply the magnetic field strength in the opposite direction. So when we have a certain magnetic field strength, then certain so this is in the direction opposite to that of the magnetic field induction, then we will have this magnetic field induction will come to 0. Then when we further decrease the magnetic field strength or further increase the magnetic field strength in the opposite direction, it will come to a certain value here. And then when we again try to increase the magnetic field strength, it will reach to a certain point, but in now the opposite direction. So this is called again the reminiscence. And so what is happening is, we need to now give a certain amount of extra magnetic field strength to completely cancel the magnetic field induction. So this extra magnetic field strength that is required to give to that material for complete cancellation of the magnetic field strength is called coercivity. So there can be different material in which, for example, here we have a low coercivity material, but it has a high reminiscence. This kind of material is called soft magnetic material. Why soft? Because you have to apply a very less amount of magnetic field strength for a large change in the magnetic field induction. But for example, in materials like this, you have to apply really a large amount of magnetic field strength for a given amount of magnetic field induction. These are called hard materials, and these are particularly used in transformers. Here you don't want for there the H field will be changing very frequently, but you don't want your B to change that fast in transformers. So there we use something. There we have to use hard magnetic materials. But in memory systems, magnetic memories, there we need to use soft magnetic material, because with a less amount of current we want to change the magnetic state. Now we have let us try to understand what is actually happening in terms of the electrons. We have studied about the density of occupied states, that n of E, it follows a parabolic behavior and it drops at the Fermi energy. Now we plot this same diagram, but in this n of E in x-axis and energy in y-axis, and we separate the two spins. This on the right hand side it has been shown a spin of particles, on the left hand side it is the spin down particles. When there is no field applied, the number of magnetic spin up particle is same as the number of spin down particles. But when we have, let us say that we start to apply an external magnetic field, then there will be certain spins which are aligned with the direction of the field and certain spins which are opposite to the direction of the field. So the one which is aligned to the direction of field are called the spin up particles, and which are aligned in opposite to the field are the spin down particles. So now what happens is, if you are aligned in the direction opposite to the magnetic field, you will have an increase of the energy. But if you are aligned in the direction of magnetic field, then you will have a decrease of energy. So now what will happen? But the Fermi energy has to be maintained. So in order to lower the energy, what will happen is, most of the spin down particles, they will try to the spin down particle they will try to align with the magnetic field and become the spin up particles. So now there is a large number of spin up particles than the spin down particles. This is called so this thing is called so now you have a net magnetic field, which is uh, a net magnetic field induction in the material. So this is how the spin of the material will align with the external magnetic field. Now let us talk something about the electron compounds. So for example, most of the conductors like silver and copper, they are in abscissa structures. So they can be like we can put they can be doped uh, in certain quantities to form something called terminal solid solution, and they will be mostly in abscissa structure. And uh, but if you start mixing, then the structure of the solid solution, it will change to a BCC structure. So but what is happening here, the composition at which this uh, change of crystal structure from FCC and to BCC, see the individually they are FCC structure, but at a certain stage they will become BCC structure depending upon the amount of alloy. So based on the alloying element, what we have is, we assign a certain valency state to the alloying element and then calculate the E by A ratio, or the number of elements on a per atom basis. Then what will happen is that at a particular level of electron filling, will have this transition from FCC to the BCC. So it is the electronic structure. So for example here, when we have so this is the actual Ne versus E. So at the Brillouin zones, or at the Bragg planes, we will have this N of E, or the number of electrons, it will increase than the free electron part. So when E by A is 1, or the valency is 1 up to here, then it is following a free electron curve. But as we increase, like let's say E by A is 1.5, so when we increase, it will now go beyond this value, and it will there will be a distortion in this N of E plot because of forming that band, and there will be more states near the Bragg plane. So the crystal structure change or the phase change occurs at specific values of this E by A ratio, and because of so this the electronic structure in that material, in this material, they will decide the phase of the material, or the structure or the crystal structure of the material. And because this electronic structure is contributing to these crystal phases or the crystal structures, these are called the electron compounds, and these phases are also called Hume-Rothery phases. Okay, so here, so if you plot this FCC and BCC, how they will look like, how the density of states will look like, it looks something like this. And based on what is the E by A ratio is, and the system will anyway try to minimize the energy. For example, in this region, the energy to form FCC is lower than the energy to form BCC. Okay, and so that's the thing, like if depending on this E by A ratio where this filling is, wherever the energy is less, for example, it is uh, yeah, depending on this E by A ratio, the phase of the alloy will be determined, even if individually both of them are in FCC lattice. Now we will talk something about how this something about the crystals itself. So let us say these are the individual atoms of the crystal. Then the uh, any disturbance of this lattice, that will create that disturbance can be transferred through the crystal through the vibration of these lattices, and that will be the speed of sound. So uh, so we know that E is h nu for photons, but in case of these vibrations, this nu or the frequency, it is replaced by Vs or the speed of sound divided by lambda, where lambda is the wavelength of these disturbances. So what can be the lambda max? Lambda max, so if we have a particle a material of dimension L, so the lambda max can be 2 times L, or this is twice the length of the material is your one full wavelength. And the lambda minimum, it is of the order of this atomic spacing. So lambda min is 2 times d, where d is this atomic interatomic spacings. And these are matter waves, and these waves are also called phonons, and these are the waves of lattice vibrations. And most, when you heat a material, most the major contribution comes from these phonons. uh, so till now we have seen that the specific heat capacity, or the heat capacity of the specific heat, it comes we have seen the electronic contribution to the heat capacity, but there is contribution to the heat capacity from phonons as well. So now there are two kinds of phonons. One is acoustic phonons, when you have a, let's say, monovalent material, one type of material you have in that entire crystal. Then the disturbance of air will propagate just like a sound wave. So those are called the acoustic phonons. But there are situations in which you have, for example, sodium chloride crystal, in which the neighboring atoms are of opposite charge. So they are like, when they start to vibrate, what will happen is it is like, it will become like a dipole oscillation, and that can interact with light. So those kind of phonons are called optical phonons. Now based upon the band gap, so we talked about the band gap and this in AK diagram, how the band structure will look like. So if we have a band structure like this, where the minima of the above band and the maxima of the lower band is at the same k vector, then it is called a direct band gap. But if there is a gap, a gap in the k vector, if they are not in the same k vector, for example, the minima of this is not the same as the maximum of this, in that case we call these materials to be having indirect band gap. And for example, when we want to have some interaction with light, then the direct band gap material can they can directly interact with photons, because photon, if you look at its dispersion relation, it is quite steep. So the k vector here has to be really 0. So these direct transitions are allowed in case of photons. But in case of indirect band gaps, there has to be some other medium which can compensate for this difference in the k vector, and that is done by these phonons. So the photon transitions will be from here to here, but it is with the help of phonons the k vector is maintained, or the momentum conservation is maintained. So that is why, since this involves more particles, photons as well as phonons, this transition is less probable less probable in the presence of a light, whereas this is more probable in case of photons. So that is why for optoelectronic materials we particularly use the direct bandgap materials and not the indirect bandgap materials. Now let us talk about another phenomena called superconductivity. It is a phenomena in which you look at the resistivity with respect to the temperature. So normal conductor, what happens, if you lower the temperature, the resistivity will decrease and it will saturate to a value based upon what is the impurity content of that particular material. But there is a certain material in which if you start to decrease the temperature, there will come a temperature at which the resistivity suddenly drops to 0 and the resistivity is 0 from 0 to this particular temperature. So that temperature is called your critical temperature. It was first discovered in 1911 in case of mercury, and there are 28 elemental metals which has a transition temperature of critical temperature of less than 10 Kelvin. And there are several intermetallic compounds and alloys have been found which have a critical temperature of less than 20 Kelvin. And in 1986, even materials which are ceramics at room temperatures, they are found to behave in a superconducting way with a critical temperature of around 90 Kelvin. So here we saw the temperature is quite crucial, but other than that, if you have this superconducting phenomena and if you start increasing, let's say this S is for the superconducting state and N is non-superconducting state. If you start increasing the current in that material, then up to certain current density there will be no resistivity and perfectly superconducting state. But suddenly if you cross that critical value of current density, then your superconducting state is destroyed and what you have is the normal conductivity. Then we have this is called the critical current density. Similarly, there is also called critical magnetic field. So below that magnetic field, the material can tolerate the superconducting material can tolerate the magnetic field, but as you increase the magnetic field, the superconducting state is destroyed and it will become non-superconducting. So what we have here is a phase boundary, which is in the three axes we have a temperature, the applied field strength and the current density, and this is the critical values of these quantities, and superconducting state is only within this region and not beyond this. There is something called the Meissner effect, in which says that a superconductor is a perfect diamagnet. That means it opposes all the magnetic fields into the material. So there is this thing called the magnetism, it will oppose the superconductivity always. That means something that is fundamental to magnetism cannot happen in the case of superconductor, and something that is fundamental to the superconductor cannot happen for the case of magnetism. The theoretical understanding of this superconductivity, it first happened in it was first given by Bardeen, Cooper and Schiffer, and they told that the superconductivity, it happens via something called pairs of electron interacting via the lattice vibrations. Okay, these pairs of electrons, so the two electrons can be separated by of the order of distances a few nanometers, whereas the atomic spacing is of the order of few angstroms. This pair, they interact with each other by means of the phonons, and what is happening is these pairs are since this idea was given by Cooper, these are called Cooper pairs, and the condition on them is that they should have opposite spin and they should have opposite k vector. Since they have opposite spin and it is a particular this pair behaves as a single entity, so the net spin will be 0 because they need to have the opposite spin. And since this is the case where we are encountering that the spin of the Cooper pair is an integer which is 0. So, but so the materials with spins with integral spins are called bosons, and phonons are also bosons. Cooper pairs are bosons. Similarly, photons are also bosons. Now, since we saw that these Cooper pairs need to have this opposite spin, the magnetic spin moment will be cancelled, and hence no magnetism. And if we try to impose magnetism on them, then the spin of the Cooper pair will start to align itself in the same direction. But when the electrons are in the same direction, they are no more a Cooper pair. So when there are no Cooper pair, there is no superconductivity. So magnetism and superconductivity are opposing to each other at a fundamental level. There are two types of superconductor based on how the superconductivity to non-superconductivity transition occurs when you vary the magnetic field strength. If the transition occurs very abruptly, so what you do from zero magnetic field strength, you apply magnetic field strength to that superconductor. At a particular value of magnetic field strength, the superconducting state will abruptly stop, and the non-superconducting state will start to will start. This is called type 1 superconductors, and will have one critical field. But there is another type of superconductivity, it is called type 2 superconductivity, in which there is a gradual transition from the superconducting state to the non-superconducting state. So what will happen? You start to increase the magnetic field strength, there will come a critical field strength 1, where you start forming small vortices of superconducting region of the normal region, small vortices of normal region or non-superconducting state in that bulk of superconducting material. And when you start to increase so that is called a mixed state. Mixed because it will have certain superconducting regions and certain regions of non-superconducting. So as you increase the magnetic field strength from Hc1 to Hc2, then the region of the normal state will start to increase, and from Hc2 onwards it will be a non-superconducting state. So this gradual transition, it happens in the type 2 superconductors. They have a lot of usages, the superconductors, particularly in the field of medical imaging. This MRI scans you might have heard. So it is magnetic resonance imaging. For this you need a very large magnetic field, and this is obtained by superconductors. Then there are other in fundamental physics experiments. For example, there is particle accelerators and colliders at CERN. They search for Higgs boson when they smash two highly energetic particles. But the way they control the movement of these particles or detect them is by having the superconducting magnets. So now, what is happening is there is a technological challenge. The technological challenge is obtaining a very low temperature, and nowadays there are ceramic materials which are at room temperature. But if you want to have a useful material, you need to have large quantity and in useful dimensions. For example, ceramics, you cannot draw it into a wire at room temperature processing. So these are some of the technological challenges, and we saw that these Cooper pairs, they are bosons because they have integral spins, and they have something called these Cooper pairs, the photons, they come into a particular category of particles called boson. The requirement is that they need to have an integral spin. And boson, it is named after Satyendranath Bose, who actually gave the idea. And so Einstein validated that idea. So it is called the Bose-Einstein statistics, the statistics that is followed by these particles. So what 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 are these particles? These particles are quantum particles. Quantum particles are identical and indistinguishable particles, but they are not subject to the Pauli exclusion principle. In Fermi Dirac statistics, they are quantum particles, but they were subject to the Pauli exclusion principle. Here, a particular state can have as many particles as possible in a given state. So now let us say that we have this energy state, energies E1, E2, E3, E4 up to ER, such that the total energy of the system is constant. And we have SI states with energy EI, that means S1 state with energy E1, S2 states with energy E2, S3 states with energy E3, and so on. Now we want to distribute n particles or n bosons in this energy states. So let's say E1 has n1 particles, E2 has n2 particles, E3 has n3 particles, and so on. Note that you cannot have more particles than the available states. So Ni is always less than or equal to Si. Now the probability of occupancy of a state at energy level Ei is given by Si over Ni. So if you have Si states and Ni particles, then the probability, what is the probability that Ei is occupied? It is simply Ni over Si. Now we want to find how that can be possible. So what we want to do is we want to look for situations, we want to fill these states with this many number of particles, subject to the condition that all of this can go into a particular box. So the way that can be done is, if you have Ni particles and Si states, then you need to have Si minus 1 partitions and Ni particles. And the number of ways in which Ni particles can be put in Si states is omega Ni, which is given by Ni plus Si minus 1 factorial divided by Ni factorial into Si minus 1 factorial. And the number of ways in which that distribution can be created is omega Wn bar is product of all the omega Ni. Now we want to maximize this W of n bar by saying that okay, the maximum value will be the most probable value and it is more than all other possibilities combined. So we will take the log of this quantity and we will try to maximize it using Stirling's approximation and Lagrange's multiplier theory. So when you take the log of this, the product becomes summation, and so we end up with this expression. So when you take log of Wn bar, we have this expression, and then we take the Stirling approximation to convert these factorials into products and logarithm. Then after some simplification, what we get is this expression. Now what we want to do is we want to take a variation with Ni. So when we take the variation of Ni and equate it with 0, then whatever the expression that we get is, after simplification, sum over I equal to 1 to R delta Ni, and this quantity that is equal to 0. Subject to the conditions that, or subject to the constraints that the total number of particles has to be same, which in terms of delta Ni it is shown as this, and in terms of energy conservation we have delta Ni Ei is equal to 0. Now we will apply the method of Lagrange multiplier to maximize this subject to constraints 2 and 3. So what we do is we take equation 1 minus equation 2 and multiply that with a Lagrange multiplier alpha, and equation 3 with Lagrange multiplier beta. So when we do that, we get this expression, and after simplification we get Ni over Si, which is 1 by e to the power alpha plus beta Ei minus 1. Now it will so turn out that beta is 1 by kbt and alpha is EF by kbt, and what we have here finally is we get an expression like this. So Bose-Einstein statistics will have this exponential factor minus 1, and Fermi-Dirac statistic will have this exponential factor plus 1. And this so mathematically it just looks like just a change of sign, but it has very deep consequences. And one of the fundamental reason why this happened is because of the presence or absence of the Pauli exclusion principle. So these two quantities, these two distributions, they assume that the particles are indistinguishable. But if the particles are distinguishable, they are classical particles, and they are given by simply P naught e to the power this EI over kBt. So there is something called, since Pauli exclusion is not valid for this kind of particles, all particles can be condensed into a single state, and these are called the Bose-Einstein condensate. Now, we have discussed that the technological challenge is coming down to a very low temperature. For example, in 1995, in rubidium atoms, when they cooled the system to 10 to the power minus 7 Kelvin, then it was first shown by this Cornell, Wyman and Kettle in 2000, and because of that they got the 2001 Nobel Prize. This 2.7 Kelvin is the temperature of the universe, and going less than that is really a very big technological challenge. So even if Bose-Einstein condensate was predicted at 1925, it took around 70 years to experimentally achieve it. Now let us discuss about some of the questions and answers of some of the question answer related to the current discussion. So what is common between MRI and particle accelerator? So the common thing between MRI and particle accelerator is that they both of them employ a superconductor as the source of their magnetic field. Since they have superconductor, they will have Cooper pair as well. The superconducting state to normal state transition is dash in type 2. Remember, in type 2 there was a gradual change from Hc1 to Hc2. Yeah, so the superconducting state to normal state transition is, this is gradual in type 2 and this is abrupt or sudden. A Cooper pair can, because in type 1 superconductor, so when you increase from 0, so this is H field. So at Hc, suddenly the transition from superconducting to non-superconducting will happen. But in case of this type 2, Hc2, it will go superconducting to non-superconducting. It will happen gradually through something called a mixed state. Cooper pair can form when electrons are several nanometers apart and interact through the lattice phonons. And it is not photons. And why not angstrom? Because like these are atomic spacings which is of the order of angstrom, and the Cooper pair electrons they will interact by these phonons. That is why they are nanometer apart. Match the following. Photons are, they have, so photons are bosons. Phonons are also bosons. Cooper pair is also boson. But Cooper pair, we know that it has zero integer spin as well. Higgs particle is also a boson. All of them are bosons. Phonons are the particles of sound. That is true. Phonons are the particles of sound. Cooper pairs have they need to have zero integer spin. That is also true. Zero integer spin. And D Higgs particle is a boson. So 1, 2, 3. And A is photons are the particles of light. That is the most appropriate answer. Yeah. So A4, B, I, C2 and D3. Yeah, this is the correct answer. The superconducting state of a material is decided by three parameters. It is decided by what is the current density, what is the magnetic field, and what is the temperature. So current density, magnetic field and temperature is the correct answer. And these things has to be less than the critical field, then only it is valid. Dash in a material is indicated by weak opposition to the applied magnetic field. In a material is indicated by weak opposition. A weak opposition means it is a diamagnetism. Remember that it has mu r less than 1 and chi negative. A material which shows magnetism only in the presence of external magnetic field is non-magnetic. And paramagnetic material is also a non-magnetic material. So if you remove this external magnetic field, then magnetism is lost. That happens only in the case of, so non-magnetic material are like, one example is paramagnetic, other example is diamagnetic. So dash causes the change in the structure. Dash to okay. In homoruthery phase, what happens is based on the electronic structure, the crystal structure will be decided whether it is an FCC or whether it is an BCC. So phonons are the vibrations of the lattice or the matter. So these are matter waves. An optoelectronic device is preferably material made of a material which is, so for an optoelectronic device we need to have this EK diagram such that the maxima of, this is K, this is E, the maxima of the valency band is just below the minima of the conduction band. This thing is called a direct band gap material, and it is important for a photon mediated transition. So a band gap transition involving both photons and lattice vibration modes. So here only, so if it has both photons and lattice vibration modes, then the probability of that happening will be less than if it were only the photons. So this we don't want. This happens in case of indirect band gap transitions. So indirect band gap, just to revise, indirect band gap transition is, suppose if you have this here, this here, this here, this is your E. This band gap is your indirect band gap. This we don't want to happen, because to compensate for this K vector there will be certain phonons involved, and we want a band gap transition involving only photons. A band gap transition involving only lattice vibration modes, this will not be optical at all. And if there is no band gap, then there is no probability, without photons the transition can take place, so photons is not involved. So optoelectronic device need to have a band gap involving only photons, and that happens in case of a direct band gap conductivity. Direct band gap. The low temperature superconductivity is explained using the quantum mechanics, including classical statistics is not possible. So uh, it will require quantum statistics if it in low temperature superconductivity, it is uh, explained by the BCS theory, which involves Cooper pairs of electrons. These Cooper pairs, since they are in pairs, they have an integral spin. An integral spin, they will not follow the Pauli exclusion principle. So this is your correct answer. And since they have integral spin, they will follow Bose-Einstein statistics. The high magnetic field can oppose or break the superconducting behavior of a material because the magnetic field opposes the Cooper pair formation. Suppose if you have a magnetic field and the Cooper pair spins are, this is magnetic field and this is a Cooper pair, let's say, the spins has to be opposite for it to be in Cooper pair. But if there is a magnetic field and it is very strong enough, so this electron is happy because it is in the direction of magnetic field, but this electron will be forced to flip its spin in this direction. So when you have the spin in the same direction, these are no longer a Cooper pair. So high magnetic field can go because it opposes the Cooper pair formation, and that is why it opposes the Messner effect as well. Because so once the Messner effect happens, because there are no spins, no free spin, all the electrons have the opposite spin and they cancel each other. But if it is not there, then it will it will oppose the Messner effect. The Cooper pairs interaction through lattice using phonon at a distance of approx some nanometers. So this we have seen. It is of the few nanometer, relatively long range phenomena. Among the type 1 and type 2 superconductors, type 2 is more preferable because this material can handle, so this can handle higher value of relatively higher value of temperature and higher magnetic field as well. And there is also higher temperatures and higher values of magnetic field, and as compared to the type 1 conductors. And one important thing is we have a control over, so there is this Hc1, Hc2. So since this transition occurs gradually, we have certain control on the amount of that superconducting behavior as well. The Cooper pair formation requires, so we have seen that there should be two electrons, and the two electrons should be of opposite spin and opposite k vector. So the correct answer will be two individual electrons with opposite spins and two individual with opposite wave vectors, two individual electrons with opposite charge. No, it is two electrons. Two electron can have same charge only, it is minus E. So this is not correct. One electron and one proton, this is also not correct. So thank you for joining. We'll meet in the next class. It is tomorrow, and we'll be discussing about all the so it will be a revision session, and we'll be discussing about all the questions and answers of all the sessions we have discussed till now. Thank you so much.